What is Connext? Connext is a modular protocol for securely passing funds and data between chains. Developers can use Connext to build cross-chain X apps or applications that interact with multiple domains, as in blockchains and/or rollups simultaneously. So it can interact with layer 1s and rollups and layer 2s simultaneously. But why does the Connext team actually think we need X apps? Blockchains do not scale to the level of volume needed for mainstream adoption. Ethereum and other programmable blockchains solve this problem by moving users, funds, and data to multiple parallel domains or sidechains or rollups. This, however, creates a challenge. It's a fragmented user experience. As in, you have people in isolated little islands all throughout the crypto universe. Similar to how YouTube users don't need to understand Google's distributed database infrastructure, decentralized application users shouldn't need to consciously think about what chain they are on or how to move their tokens and their NFTs and transactions between chains. In other words, applications should abstract the multi-chain experience by becoming X apps and do so while retaining the security and the trust minimization properties of the underlying chains in which they live and operate on. And I know we need this. I can't tell you how many people, including myself, have been victims to sending their tokens to an exchange or to another wallet, only to realize that wallet could only access those tokens on a certain network. Connext is built with 3 core design principles in mind that make it the best option for developers who are looking to build X apps without compromising on trustlessness. The first thing is its modularity. Connext utilizes a modular hub and spoke architecture, which derives its security from Ethereum Layer 1 and plugs into the battle-tested canonical messaging bridges that underpin the security of each Ethereum-connected domain. Messages in Connext are added to a Merkle root generated on each spoke domain, which are then optimistically aggregated into a singular root on Ethereum Layer 1. In the event that fraud occurs, then the system falls back to using the canonical messaging bridge for each chain ecosystem. So in other words, to make it more simple, a message passed between Polygon and Optimism is secured by a proof that is posted to Ethereum and verified by the Polygon proof of stake bridge and Optimism rollup bridge. Similarly, a message passed within the Cosmos ecosystem is verified by IBC, Inter-Blockchain Communication Protocol. This mechanism gives developers the best possible trust guarantees for whichever chains they actually want to build on. For fraud to occur in our Polygon to Optimism example, there would actually need to be a compromise of Polygon or Optimism's canonical bridges, as well as Connext's fail-safe mechanisms. The second principle in Connext's design philosophy is security. Bridges and cross-chain messaging are some of the most critical infrastructure in the space, with a high potential risk for catastrophe in the event of hacks or bugs. In the past 18 months, almost $2 billion has been lost to bridge hacks, so this is a problem that's as big as rug pulls. Connext utilizes watchers, automated off-chain actors that observe the network and halt message passing in the event that fraud or a hack is observed. This ensures that damage due to the failure of any individual part of the network gets minimized. Additionally, Connext follows a strict philosophy of secure development, requiring rigorous external review for code changes and working closely with the security community to educate auditors on bridge security risks and collaborate on creating best practices. The third part of Connext's design philosophy is simplicity. Migrating to a completely new multi-chain development workflow can be a pain in the ass, just like that sentence. Rather than reinventing the wheel, Connext tries to mimic and extend existing development patterns as much as possible. The protocol implements a single simple primitive called XCall, which allows devs to asynchronously interact with contracts living on another chain or rollup, similar to how you would call a contract living on the same chain or rollup. Connext additionally plugs into the tooling and supporting infrastructure that is already widely used in the ecosystem. If you do have a development workflow that isn't well supported by Connext, you can even reach out to them on Discord or by emailing them or messaging them, and their community will be willing to help you build for it. But what can you build with Connext? The simple answer is pretty much anything. So some members in their community are building things to execute the outcome of decentralized autonomous organization votes across chains. They're using it for lock and mint or burn to mint token bridging. They're using it for aggregating decentralized exchange liquidity across chains in a single seamless transaction. That's fucking insane. They're doing cross-chain vault zaps and vault strategy management, lending funds on one chain and borrowing on another. The users of Connext are bridging Uniswap v3 time-weighted average pricing to every chain without introducing oracles. They're doing NFT bridging and chain-agnostic NFT marketplaces. Again, that's another huge thing. They're also storing data on Arweave or Filecoin directly from within an Ethereum smart contract. If everything I just said wasn't overwhelming enough, there's so much more to dive into in regards to Connext and how it works. The Connext protocol is composed of a set of smart contracts and off-chain agents. Connext smart contracts are the interfaces between the protocol and the wide gamut of different users in the ecosystem. There are contracts for handling XCall. There are contracts for managing asset registration and provisioning liquidity for routers and stable swap liquidity pools. Connext dispatches and handles messages related to sending funds across chains, custodies funds for canonical assets, fast liquidity, and stable swaps. Next is messaging. The various contracts required to manage Merkle routes containing hash transfer data and send them through a hub and spoke architecture. The messaging architecture includes a connector. A connector is an abstraction around an underlying transport layer. The iConnector interface requires a process message method implemented for handling incoming messages. The routers. Routers are liquidity providers that enable instant liquidity for the user on the destination chain in return for a fee. Anybody can participate in the protocol as a router, and there is no minimum liquidity required. Routers provide a crucial service to the Connext protocol. Next is sequencer. The sequencer collects bids from all chains and randomly selects routers to fulfill them. Any number of routers can fulfill a single transaction, which is especially useful for large transfers. The sequencer will post batches of these bids to a relayer network to submit them to chain. Relayers. Relayers are a decentralized network of infrastructure operators that can execute smart contract transactions on behalf of a user in exchange for a small fee. Because the last leg of a cross-chain transaction requires execution on the destination domain, relayers play a crucial role in completing the full flow. Currently, Connext is using Gelato as their relayer service. So for transactions to actually go across chains through Connext, they either travel through either a fast path or a slow path. For a cross-chain message to travel through the fast path, it must abide by two requirements. The first requirement is that the transaction is bridging tokens only and no call data, or the call data included with the transaction is unauthenticated, as in anyone is allowed to call the function on the target contract. The second requirement is that routers are providing sufficient liquidity of the bridge token on the destination domain. We sometimes refer to this as the availability of fast liquidity. If fast liquidity is not available, then the message will always go through the slow path. So given everything that Connext actually does, we gotta actually talk about bridges. So what is a bridge in a crypto blockchain context? A bridge can also be called a cross-chain messaging protocol or interoperability network. It's a system that relays information between blockchains. While there are many bridges out there today, every bridge has the same core structure and components. So every bridge is made up of pretty much 4 layers. One layer is called the transport layer. The whole function of this layer is to read root or hash of data on the origin chain and post it to the destination chain. The second layer is verification. The function of this is to ensure that the data in the transport layer is correct. The third layer is the execution layer. The function of this is to generate Merkle roots or hashes on origin, so that you can prove against the root and execute the target function on the destination blockchain that you're transferring your tokens to. The fourth layer is the application layer. This application layer handles specific use cases such as token transfers, NFTs, governance, and more. So currently, the vast majority of generalized bridges out there today are monolithic. This means that they are tied to a specific verification mechanism that is implemented as a core part of the bridge construction. Connext is the first example of a generalized cross-chain messaging mechanism that is modular, plugging into the best available verification method for a given ecosystem. So to understand why Connext is designed the way that it is, you have to explore the concept of clusters. A cluster is a sovereign set of domains that share security and can communicate with one another using trust-minimized methods. For example, Ethereum and its rollups form a cluster. Cosmos chains are also another cluster. Singular monolithic chains such as Solana are also their own cluster. So they're their own little worlds or communities. You have to imagine it that way. They're their own little isolated islands within the cryptoverse. When we were talking about message verification, we broke down the different methods that actually exist to secure a message that travels between 2 different domains. As we spoke on, the best available mechanism for verifying messages is different based on the specific pair of blockchains we want to communicate between. For example, between a rollup and its layer 1, the most secure verification mechanism is to use the rollup bridge itself. The security of a domain is always the security of its weakest link. This means that any method of passing messages to a rollup that isn't the rollup bridge introduces at least some trust assumptions and security overhead, which in turn weakens the benefit of using a rollup versus a less secure domain such as a sidechain in the first place. On the other hand, the most secure way to verify a message that passes between 2 discrete chains is a light client, ZK or otherwise, so like ZK rollups. Light client implementations exist in some places, but not everywhere yet, and it's highly unlikely that a single light client protocol will win every single pathway between sovereign chains. It's more likely that multiple protocols will exist in one ecosystem, which is why interoperability is so crucial, which is why something like a modular application to enable and elicit this is so necessary. Modular bridges make the verification layer and potentially other layers of the bridging stack pluggable. By doing this, they can leverage existing methods of message verification wherever possible. This gives the best possible security for applications that may want to interact with multiple domains or blockchains or ZK rollups or layer 1s and layer 2s simultaneously. The most important component of any cross-chain messaging system is how messages are verified across domains. Externally verified bridges rely on a third-party set of actors to attest the correctness of data that is transported between chains. This is typically represented as a multi-sig MPC system, proof of stake validator set, or an oracle or relay. External verification is easy to extend to any chain and can support generalized messages at low latency. However, the security of a message passed between chains fully relies on the verifier set. This means that the security scales with the size of the set. In most cases, externally verified badges have far less security than the underlying chains, implying that they are not trust minimized. External bridges with large validator sets and staked incentives like proof of stake systems are more secure than their smaller counterparts. The next method is optimistic bridges. Optimistic bridges use fraud proofs to ensure the validity of data relayed across chains. Every message that passes through an optimistic bridge remains in a pending state during the dispute window until it is considered valid. During this time, watchers can dispute the message if the data is incorrect. Optimistic bridges assume that there is at least one watcher online somewhere that can send a transaction to the chain. They also assume that watchers will not abuse their position in order to censor the system. Censorship risk can be minimized using economic disincentives, but there is a lot of trust placed in watchers in optimistic bridges. In a natively verified bridge, a chain's own validator set verifies information coming in from another chain. This happens by implementing a light client of one chain within the virtual machine of another, typically within a ZK snark to keep expensive computation off-chain. Because light clients verify consensus but not the state transitions of the block itself, the latter requires data availability. They assume the existence of an honest relayer who can give them the correct block from a connected chain. This makes them vulnerable to attacks where the validators of one chain produce an invalid block, for example, through a majority attack or 51% attack to spoof a message through the bridge. This honest relayer assumption of light client-based bridges is the key point behind Vitalik's often discussed multi-chain, not cross-chain post. Natively verified bridges have an additional trade-off in that they require custom work for each chain with a new consensus mechanism. For some domains, for example with rollups, there may not be a light client-based strategy for bridging that works without additional trust trade-offs. Despite the above, natively verified bridges, regardless of whether they use ZKPs, are the best mechanism for moving data between two discrete blockchains. Locally verified bridges are a special case of bridging where only the parties involved in a given cross-domain interaction verify the interaction. This is typically done through schemas like atomic swaps. The challenge of locally verified bridges is that they require the liveliness of all parties involved in a transaction, degrading user experience and making it impractical to execute transactions that involve more than two parties. This further means that there are only some types of transactions that are supported. For example, a peer-to-peer transfer is possible because there are only two parties involved. But many types of peer-to-contract interactions would not be possible as every chain user would be involved. Local verification techniques are typically used in conjunction with other mechanisms such as optimistic bridges in order to improve latency. Rollups are another special case. Rollups exist specifically to solve for the honest relayer assumption that exists with light client-based bridges. They do this by creating a strict hierarchy between the parent chain, the layer 1, and the rollup that exists on the layer 1. With all rollup data being available on the layer 1, this allows the layer 1 to run a full client directly, verifying the state transitions of the rollup itself. Rollup bridges are the most secure mechanism to communicate between any two blockchains, domains, layer 1s, layer 2, period. However, they can only exist, unfortunately, between a rollup and its layer 1. So Connext provides you XERC20 tokens. XERC20 tokens are cross-chain Ethereum tokens, which can be transferred with no slippage across chains without compromising on security. Today, when you want to make your token available on multiple chains, you have to either provide a crap ton of liquidity to a bridge on each chain, and even after providing all that liquidity, users still will have to eat some slippage when making that cross-chain transfer. Or you have to mint an entirely new representation of your token through the bridge, locking yourself into that bridge and its security model forever. XERC20s are natively cross-chain without compromise. This makes your token transferable across chains with zero slippage whatsoever. The tokens are deployed and fully controlled by you, the token issuer, including the ability to set rate limits on a per bridge basis. XERC20 tokens, when bridged through Connext, are secured fully by Ethereum Layer 1 and the canonical bridges of each and every chain. And soon, XERC20s will be fungible against the token representations minted by canonical bridges like rollup bridges, Polygon proof of stake bridge, etc., etc. Connext is actually pushing pretty hard for the industry-wide adoption of XERC20s as well. And if you'd like to learn more about that, I'm sure I'll release an episode about it. I won't even give you a link. You guys hold me to that. The steps to actually set up an XERC20 are pretty straightforward. So all you have to do is choose a home chain for your tokens or whatever chain your token is already deployed on. After that, you deploy a mintable or burnable token representation on the other chain that you wish to support, that you wish to bridge your tokens to. And then after, you simply allow bridges to support your XERC20 with custom rate limits. To enable Connext as one of your allowed bridges, all you have to do is send your token addresses to the Connext team. After that, you would give the Connext contracts rights to mint your token, and then you would work with the Connext team to signal to Connext routers to supply fast liquidity for your token. It's entirely possible for you to also run your own router to supply fast path liquidity in Connext if you would like to do so. But if this is a problem for you, they already have their own ecosystem of routers that can work with you to add liquidity for your token, and that's also just much faster if you just want to speed up the process. Routers are highly capital efficient and they do earn money from fees. And so the network only needs about 1/8 of the expected router's 24-hour volume in liquidity in your token. So if that is something of interest to you, you should contact them. You should actually reach out and build. We need more people building in the community. Connext combines the security of bridging through canonical bridges like Arbitrum and Optimism and Polygon into a single easy-to-use developer interface. Connext batches data associated with cross-chain token transfers into Merkle routes. These routes are passed on to Ethereum Layer 1 from each chain through canonical bridges. Then they're further batched on Layer 1, so onto base layer Ethereum, and then they're passed back to each subchain or parallel chain. This forms a cheap, trust-minimized message highway through which you can communicate between chains. And for tokens specifically, Connext supports burning and minting across chains by communicating through the underlying messaging highway. Messages through Connext that are passed through Ethereum can take 1 to 3 hours to arrive across chains, which is too slow to provide a great user experience. That's why Connext routers are there, the node operators of the network, who cut this time down to 45 to as much as 180 seconds, so 3 minutes. By fronting liquidity, so paying the fee in advance to the user immediately and being repaid by the protocol once everything actually processes on the network. Routers are charged a 5 BPS flat fee for this service. But why should you actually use Connext for cross-chain tokens? Well, there's a few important reasons why they're different from the rest. You see, Connext has a long history of prioritizing security and trust minimization over everything else. By delegating cross-chain message verification to canonical bridges, Connext is the only messaging bridge that will give users the trust guarantees of the underlying chain. For cases where no canonical bridge is actually available, Connext expects to plug into something like Hashi, a project which tackles message format standardization and security trade-offs being made by applications and bridge designers. Connext has gone through 4 audits, including Code Arena, Spearbit DAO, and Macro. Unlike other token bridges, Connext prioritizes giving you sovereign control over your own projects as assets. They actually advocate for you to deploy and retain full control over your own token implementations on each chain. This means you retain the ability to delist Connext if you don't actually mess with what they're doing. If you don't like their work, you can cut them off. Or you can choose to list other bridges as well in addition to Connext and use more than just one. Why not? And soon, they'll also be making it possible for Connext tokens to be fungible against token representations deployed by the canonical bridges themselves, the original chains which they derive from themselves. This means that regardless of whether a user sends a token through Connext to Optimism or through the official Optimism bridge, they are guaranteed to get the exact same asset. Chain abstraction is one of the flagship use cases of Connext. Chain abstraction allows a dApp or decentralized app to execute logic from any chain without requiring users to switch networks. It can allow them to sign transactions on a different chain and spend gas on a different chain. This pattern can be used at high layers to fully abstract chains from the users, removing the need for users to consciously have to think about what chain they are on. And in my opinion, this is what we need industry-wide to actually enable the mainstream adoption of blockchain. Nobody needs to know all the complicated server mechanisms and hosting and data involved with Google's hosting of videos on YouTube. You don't need to know all that shit. All you need to know is you can go on YouTube, click a video, and it starts playing. Same with these blockchain decentralized applications. You should be able to know the link to the dApp that you want to use, or open the app on your phone or on your computer, and then just start using it. And if the application needs to do all that switching in the background, cool, fine, but you don't need to interact with it if you don't want to, or if you're not gaining added value for interacting with it on the back end. Like, fuck, I'm tired of losing so much money due to trying to move the exact same token throughout multiple chains just because I don't want to get slaughtered by gas fees. We talk about decentralization, but gas fees and transfer times are absolutely killing us. And all the confusion in between dealing with these islanded communities, dealing with all these chains now, which is fantastic because it means the community's growing, but it also means everything is completely fragmented right now. It means that we really need to just see more interoperability as opposed to anything else. That's why I think Connext is such a great project, and that's why I made this freaking episode, and that's why you should fucking listen to me. If you don't want to do research, I'll do the research for you and I'll sing it to you. Anyways, I'm Andrew, the XRP Maximalist. Thank you for listening. Give me great projects and then let me actually dive into them. And if they are worth doing a deep dive into, I can at least record it for you and do all the hard work so you don't have to. Anyways, I'm having a great day. I hope you are too. Take care.